6G-XR Demo 4, we have sustainability aspects of multimedia communications or mobile networks in focus here. The title of the demo is End-to-End Application and 5G RAN Optimization based on green energy availability. And I will start by presenting some of the, let's say, technical enablers that we have included in this demonstration. And starting from the project work point of view, we have had a dedicated work package for the sustainability topics. VTT have implemented the demonstration here, but there in the project also the University of Oulu and Nokia have been contributing to the development of the technical enablers. So we will be presenting the sustainability point of view in this demonstration as a whole. Just to mention also for these sustainability topics, we have utilized the enablers that have been implemented in the demonstration extensively also in the open calls. So we have had several third parties also contributing and testing these functionalities with their products already during the 6G-XR project as well. Starting from the technical enablers, the first building block of the demonstration is the energy measurement framework that enables us to monitor the functionality of the mobile network components from the point of view of the energy consumption. So we have the capability to monitor the whole network end-to-end chain in real time and see how much each of the components are consuming energy at the different configurations in the network. The second part of the demonstration is the energy production part. We have implemented and deployed local renewable energy system at the test facility where the demonstration is running. We have solar panels providing local renewable energy. We have a battery system that can store the generated local renewable power for the nighttime use, and we have grid power or grid energy available as well. And by intelligently switching between these different power sources, depending on the energy need in the network, we can, let's say, enhance the sustainability of the end-to-end communication in different ways. The network architecture that we are using is a 5G network comprising of one microcell providing the overall coverage for the users. Then we have two capacity cells, hotspots, providing extra capacity for situations where there are multiple active users transmitting or receiving video at the same time. Depending on the need from the users, we can switch on different energy saving features in the network components or in the base station, so that we can play between the maximum capacity and maximum saved energy at different times. We also measure the energy consumption of the user devices in order to get the end-to-end view in the demonstration. So we measure also the energy consumed by the handheld or battery operated devices in different configurations. And in order to have a realistic traffic for the system, we follow a 24-hour traffic model where the load in the network is lowest during the nighttime and increases during the daytime, having the peak hours focused on during the 8 p.m. At night time period, which is let's say a realistic assumption for a commercial network operating in the city city area. And based on this traffic profile, we generate the test traffic that we also show in the demonstration here. All these components produce data that we take into a central controller component that estimates the need for the resources in the network, how much we need to save energy in order to comply with the energy availability restrictions coming from the production system, and also we can, through the central controller, also modify the quality of the video that the clients are receiving. So we can modify both the operation of the energy consumption versus capacity trade-off of the mobile network, and then fine-tune the application, the video quality, in order to meet the quality of service expectation of the users where we have a lower amount of energy available for the network operations. And the functionality of the demonstration as a whole goes in the steps shown here. So first, for each of the starting hours, we generate an energy budget based on the availability of the local renewable energy and the electricity price from the grid. And based on these two main parameters, we set a limit for the mobile network, how much energy it can consume during the next hour. Based on this limit that we calculate, we decide the energy saving features we need to activate in the base stations in the network, and also the video resolution for the clients to receive during the next hour. And based on these calculations, we configure the network for each starting hour, and then monitor the energy consumption and the performance of the network during that time period. And if we during the monitoring phase, if we see that the quality of service of the clients are not met for the next hour, we can then adapt again the video resolution together with the energy saving features of the G-Node B. So for each hour, we run this loop of deciding the threshold for the energy consumption, and based on that limitation, we try to optimize the parameters of both the network and the application, so that we get the maximum quality of service with the minimum amount of energy.
The dashboard visualizing the demo functionality has several panels showing the data related to the different system components. The energy production section of the dashboard shows the availability of the locally produced solar energy, as well as the price of the grid energy. The power consumption section shows the power consumption of the network infrastructure, including also the end-user devices and the video clients in this demo. The central controller component in the network infrastructure takes this monitoring data and decides the system configuration for the next hour. The hourly energy budget is based on the energy production data and defines the maximum allowed energy consumption for the next hour. Both the network configuration and video application settings are changed based on the central controller's optimization decisions as shown in the panels. The run state is a combination of different energy saving methods that can be activated in the equipment, and the application state defines the resolution and bitrate used for the video content. When the network configuration has been set for the next hour by the central controller, the end-to-end power consumption, as well as the end user's quality of experience, is monitored. For the video application used in this demo, the monitored KPIs include experienced throughputs, delays, and the state of the video buffer. If the power consumption of the network infrastructure exceeds what is defined in the energy budget, or the quality of experience is unacceptably low, the RAN and the application states can be reconfigured by the central controller.